Good morning, afternoon, or evening, depending on your time zone. My name is Stanislav Fort, and I'm a PhD student at Stanford University. I'll be presenting our project called Deep Ensembles, a Lost Landscape Perspective that I worked on as an AI resident last year at Google Research, together with my amazing collaborators Hui Hu from DeepMind and Balaji Lakshminarayanan from Google Brain. This talk is primarily based on a paper called Deep Ensembles, a Lost Landscape Perspective that we presented last year at the Bayesian Deep Learning Workshop at NeurIPS 2019 in Vancouver. The core question we're trying to address in this paper is the empirical observation that despite their amazing promise, Bayesian neural networks in their scalable, useful form are typically outperformed by simple ensembles of individual neural networks that were trained independently from independent initializations under the influence of independently chosen random batches of data. Let's discuss the general setup right now. We're mapping an image, in this particular case, a cute tortoise, using a neural network parameterized by a high-dimensional vector of parameters W into a probability vector P that later gets mapped into a scalar valued loss L. The connection between the weight vector W and the scalar valued loss L is called the weight space. We can imagine the lost landscape as a high-dimensional landscape of hills and valleys in which the gradient descent is looking for the deepest valley or the highest hill. Two solutions in this space can be compared using the angle between the two weight vectors, and we find that between independently initialized and trained runs, these things are roughly orthogonal, so 90 degrees between those. Whereas within the same training run, these weight vectors are near parallel to each other, given the high-dimensional nature of the landscape they're moving in. Another similarity notion that we can study is the function space similarity, where we map the high-dimensional parameter vector W into the predicted probability vector P. A key insight is that equal loss doesn't mean it's the same function. When we look at a function space distance between independently initialized and trained networks, we see roughly they're the same distance from each other on the left-hand side, whereas within the same training run, we see that the predictions at epoch, let's say 10 and 20, are quite similar. What we're looking at here is the t-SNE embedding of the prediction space of three independently initialized and optimized runs, the red, green, and blue run. We see that within the individual training trajectory, the predictions are quite similar to each other, but between the trajectories, there is a big distance in the function space. At epoch 60, we'll start adding the points that are nearby in the weight space using different sampling algorithms, and we see that what is nearby in the weight space is also nearby in the function space. On the right-hand side, we see four typical ways of sampling the subspaces around the tip of the optimization trajectory, which is the random subspace, the dropout subspace, the diagonal subspace, and the low rank normal subspace. We see that for all four cases, we are still nearby the end point of the trajectory, despite our effort to get a diverse set of functions. What we're plotting right now is the exchange between prediction diversity and accuracy. We can see that on the x-axis we're plotting test accuracy, and on the y-axis diversity as compared to a reference solution. The reference solution is a single less than 20 trained on CFAR10 to 90% test accuracy, and compared to itself, it's got zero diversity, so it's on the y-axis at 0. When we add independently initialized and trained solutions, we can see that they have roughly the same solution on the x-axis, which means the same test accuracy, but on the y-axis they're quite high up. That means they're quite diverse as compared to the green star solution. We can add the lower limit and the upper limit that comes from theory. We can start adding subspace samples from the neighborhood of the green star in the weight space. First, let's add random points. As we get further and further away from the green star in the weight space, we're getting more and more diverse, but we're losing accuracy as we do so, and we're not hitting the island of the independently initialized and optimized solutions. We can add more complicated ways of sampling that neighborhood, for example, dropout subspace or simple Gaussian subspace, but they follow roughly the same trajectory in this diversity-accuracy trade-off plot. We can add another method, in this case rank for Gaussian, but we can see that we never reach the island of the independently initialized and optimized solutions. So the trade-off between diversity and accuracy for these subspace sampling methods is inherently worse than independently sampling, optimize using initializations and independent training. To verify the validity of the separation between the ensembles and the subspace methods, we ran our experiments on CFAR10, 100, and ImageNet. Independent initializations will take us to two independent modes. These modes might be similar in terms of their accuracy, but their function will be quite distinct. This is a real network version of the previous cartoon showing the very similar structure. We know these modes are actually connected, but these connections are really hard to find at random. So what we can do is we can sample the local modes better using subspace methods, getting a better estimate of their center, therefore increasing the accuracy a bit. Or we can do an independent sample of each mode, as we normally do with a single run, and then ensemble them. Or we can do the best of both worlds and do a better estimate of the local center of the mode and then ensemble those centroids. We show that the best of both worlds approach increases the accuracy and calibration even on ImageNet. In summary, scalable subspace variational sampling primarily explores a single mode due to lost landscape geometrical structure that constrains it. It trades off accuracy for solution diversity suboptimally as compared to vanilla ensembles. Combining local weight averaging and global ensembling actually provides best of both worlds. Thank you very much for listening.